Hello everyone, welcome to today's live session. Before starting today's live session, I will discuss about first 10 minute or initial why I am discussing about this topic, why compile and IR. In my first live session, I discussed about we have a high level language source code and it get converted into executable. Who does that? The answer is very simple. This is done by the this is done by the tool chain. We have also seen little bit, not much, difference between tool chain versus compiler. If you have not watched that session, you can go and watch it. Then in my second live video, I discussed about compiler take .i as input and generate .s or a assembly as an output. Here .i means a file generated after a preprocessed one. So who does that job? That is done by the compiler. So overall, what compiler is doing, it is taking .i file is the input and generating .s file. And also in that video, we have opened the compiler as a black box into three parts. The part one as front end, the part second as middle end, and the part third as back end. So here, when I say here front end, what does front end mean? Whenever the first pre-process or first phase of compiler comes, this .i file is taken by the front end and we generate here an intermediate representation which is neither a high level language or neither a assembly. It's just in middle of somewhere. We will see how it look like, and this IR is given to the middle end as input, and this middle end then generate optimized IR, and this optimized IR is given input to backend, and this backend then generate what? This optimized IR is then we get a assembly. If you see, if you, in your mind there might be a question why we are not directly converting our source code into assembly, why we need to generate IR, why compiler need IR and why we need to generate IR. So that we are going to discuss here about completely. So first of all, see, if we are using a compiler such as clang, let me first remove all this thing. So the question should be, from high level language you can directly generate assembly, then why we need IR? That's so confusing, right? Why we need an IR? So in this live session, we are going to discuss here about this topic. If you want to go in more detail about other two topics, you can watch my previous videos. So let's see here. Before jumping into that, let's see how IR will look like. Here is a terminal, and let us suppose hmm, let us suppose this is our simple code of just we are returning some variable. If you want to generate IR, then we can just use clang -s -o out.ll. It will okay, I think the file name here is different. Let me take that as input, not the LLVM.ssa. So here, if you see, after using a hyphen lsltr, it also shows the timing which get data is generated. If you see the date, then if you see there is one out.ll file generated, you will see generation of such file, right? This particular file, if you see, it's neither a you can think of it is you have written what, if you see the source code, the source code is hmm, wait a minute. Source code is some simple. What is the source code? If we are it's greater than 0, we are returning 10, else we are returning 20. That's very simple. So here, if you see the IR, in the IR, we are doing same thing with just ICMP. ICMP as for comparison, and it's taking values from the variable 4, and we will this what you will see here. It's called a virtual registers in LLVM terminology. So in IR, so here percent 4 here means if you see percent 4, it is loading from PTR2 and PTR2, and similar way you can see if this two branch has been generated 6 and 7. So if you see the semantically both are equivalent. What are both are equivalent? Your IR and source code. So the now question is why compiler need this IR. We are going to discuss here about. Let's imagine for that purpose, uh, for that purpose we will do a very simple experiment. Let us suppose we are a compiler developer whose work is to write a programming tool to convert a source language into assembly. What will happen every time? And let us, right, there is lot of high level language, not just one. There are multiple high level, right? There are multiple high level languages. Multiple high level languages are C, C++, Java, Rust, etc. And we can name n number of them. And multiple hardware as x86, ARM, RISC, V, Power PC, and AVR, or multiple hardware are there. So now think of, we are just writing a tool whose work is to convert source code to what? Assembly language. So which source code we have? Let us first take an example of C. So from C, we are trying to design a compiler which can convert to ASM. So let us suppose if there are n hardware, then we have to write n backends. Backend here mean to from where we are converting source code to assembly. So here we have to write for C to translate to x86. Then we have to write C translate for the ARM. Then we have to write for etc hardware. So let us what we will do currently. We won't stick to one thing. What one thing I mean here? I will not take your hardware name or in language name. I will think of some example and as a variable name so that you can get better understanding. Let us suppose we have P, we have one language as L, and we want to convert it to one hardware as H. So in that scenario where we have a language L and we want to convert it to the H, we have a one language as L and we want to convert it to the one language as H. In that case, we have one language as L and other language as H. In that case, what we have to do, we have to generate, we are trying to generate assembly for the H. Now let us suppose tomorrow one new hardware came, then again we have to do multiple things to generate for H1. Similarly, again we have to do for H2. Now new hardware came, So similarly, let us suppose if in that time particularly in market n hardware are present, then we have to similarly create backend for all the hn from h1 to h1. Now let us suppose this language is also changed. Language, if you see market have C++, multiple languages, so also language will change. So this language is changed from L1, then we have to again create languages L2 and L3 till Ln. Now see, I won't take till n, I will take now three languages and three hardware, and to explain much better way. Let us suppose our first language L1 is there, and for that purpose we have to convert into a three hardware as H1, H2, H3. Then total how many compiler we have to write? First for this, second for this. So total three compiler. Let us suppose I have now language L2 and this hardware same H1, H2, H3. So again for that purpose I have to again translate them to assembly as 1, 2, 3. So total if you see there are two front end. If we will make them as, if you'll see here number of front end or number of the languages, we have two languages, and number of hardware which we have is three. Then we have to write how much time the compiler, first, second, third, fourth, fifth, sixth, total 6 time. So we can tell it as 3 cross 2 time is equals to 6 time. We are total creating compiler for 6 time. So but here in each case we have to do a lot of redundant work. To what we are doing, our compiler aim is to take .i file and generate what? Generate assembly. So when compiler is taking .i file as input and generating assembly, in that case, every time a new language is coming, then if suppose tomorrow again one more language come, then again for that purpose we have to write three assembly for them. Translator which can convert into a three different form of assembly. So again there will be total how much? Three assembly. So it will be again 3 cross 3. So if this scenario comes to be happen and there are total m front end and n back end, then we have to create or maintain compiler m cross n, which is very difficult to create, and a company have to spend a lot of their the company have to spend a lot of money just to maintain those compiler, and maintaining them is again a tedious and challenging part, because there may be chances that the same front end error are there in everywhere, same back end error are there in everywhere, and the compiler portability will also decrease. Let us suppose now for C you are using different compiler, C++ you are using different compiler, for risk you are using different compiler. Then what will happen again, you are when you want to convert to uh, when you are convert to x86 you are using different compiler. Now you want to convert C++ to, let us suppose, now you can see the problem much better way. Let us suppose you are using one compiler for C, and that role of the compiler is to convert for the x86. Then you have changed your laptop or you have changed your system hardware. Now again for that purpose you are again using C, and let us suppose here your compiler using A. Now for if you want to convert to risk, you are using compiler as B. Again for if you are using here C to XYZ architecture and you are using compiler C. So for even user purpose this is difficult. For people who want to do something, they also have some difficulties. So overall what is happening, you are doing redundant work, there is no portability, and even for user, for every new things which is coming they have to do everything from the scratch, and there is no thing as modularity. So what people suggested, what why not we come to approach, instead of creating one language as C, we can generate one IR, and then we will translate this IR to hardware. We have a language what we'll do of that language, we will convert it to IR, and from that IR we will generate a hardware assembly. How this design help, let's see. Let us suppose instead of we have three language now L1, what I did, I just created L1. Hey, L1 go, L1 go, and we have three hardware, H1, H2 and H3. L1 we have three hardware, then IR, then we have a three hardware, L1, L2, L3. What I did, instead of just directly converting to L1, L2, L3, I converted to IR. So the IR for all the three will be same. This IR will be now, we have to write a language, we have to write tool to convert it IR to L2 and L3 has hardware. Or much better way we can say that, see, we have a language as L1 and we are translating it to IR, and once we have translated to IR, if we have a three hardware as H1, H2 and H3, then we have to write a logic for translating IR1 to, let's say, make it as, let us first translate on what we are doing, the second what we are doing, third what we are doing, and fourth what we are doing. So again, if you see our, for if you see one design, for that work is increases. Now let us suppose if new front end is coming L2, then we just have to take care of what, we just need to translate L2 to the IR, and other things already done. Now a third language is coming L3, then what we have to do, we have to just write this, we have to convert L3 to the IR. We don't have to maintain a separate pipeline of hardware, and due to this what is happening, the compiler is completely dependent on IR. So due to all these things, what happens, so our design from M cross N is changed to, how many we have made, see, total three, we have three front end and how many back end, three back end. So if you see, we are just maintaining 6, 3 plus 3, 6. How 6? First translation we are doing here, second here, third here, fourth here, fifth here, sixth here, or you can name it anyways. You can just count from anywhere, from top to down or bottom down, or from front end to back end. So, but here if you see the design, M cross N has changed to, M cross N is changed to M plus N. So here the maintenance has been decreased. Maintaining, let's suppose now you have 10 front end and 5 back end. If you are not generating IR, you have to maintain 50 different variant of compilers, but with IR you have to maintain 10 plus 5 equal to 15 variant. So this is easy to maintain, that this 50. So that's why people have switched from traditional way to modern and converting their compilers to the what, IR. So what is happening now, they have designed, they have created a simple grid design today's nowadays people. What they are doing, uh, so what I discussed in complete season till now, if a compiler is directly translating any coding language, let us see, let us take an example of C to assembly, then we have to create C for x86, then C for ARM, then C for RISC-V, and C for different hosts such as 64 or 32-bit. Again, for 32-bit we have to maintain other thing, and so on. So, and again, if a new language is coming, we are doing the redundant work again and again and again and again. So, the total, if there are 2 front end and 3 back end, then we have to maintain it till M cross N equal to 6 times. But due to IR, what is happening? We are removing our redundant work and we are creating till M plus N. This is one thing, and let us suppose we have generated IR. So what is happening? We are also not touching the here different field. How? Let's see. IR, and then from IR to different form of hardware H1, H2, H3, and H4 as hardware. Now, if I am, let us tomorrow, I have L2, L3, and L4. So what I'm doing, I'm translating it to IR. That one code I am writing. So this is mostly called as front end. And from here, IR, this divided, we can divide in two part, optimize IR, but let us keep in one phase only. Now, let us suppose tomorrow new hardware comes. If tomorrow new hardware comes, then we don't have to care much. We just have to add here one translation unit H5, and again we don't have to the redundant job of doing all these things. These all things will be linked to this. So if a new hardware is coming, we just need to write a translator unit for converting IR to understand hardware 5. They don't need to write a code for roll from scratch. This is one is better design approach. So if every new language comes, we have to rewrite backend for all hardware initially. But with IR, every new hardware comes, we just need to rewrite IR translator for that hardware. We don't have to touch the front end. So due to that, what will happen? They are now decoupled. Decoupled in the sense we can now easily remove the front end part into different place and middle end part to different place. So due to this, the error fixing and design also got improved. With intermediate representation, what happened? The compiler split it into three part: front end, middle end, and back end. So what the thing is here, what we are doing from source code to the IR generation, it called as front end phase. And this from IR, we optimize IR here to give more semantically equivalent and better performance IR by middle end. And this translation of the optimized IR to back end is done by the front back end. So our design from M cross N changed to M plus N. So we have to do here less redundant work. We can add new languages, only write front end, and we can add here new hardware. And portability also increases due to this. Also better optimization, another thing we can think of. So that's why modern compiler does not translate languages directly into assembly. What they do now, they convert IR to, what they do, they first convert your front end to IR and from IR to assembly. So this is where the LLVM comes in. So in next my live tutorial, I will discuss about what LLVM is and why the tech industry switched to LLVM, and then where does LLVM actually fit in here. So if anybody have any question, they can ask. I will wait for 5 minutes. If no question, then we can just end the discussion here. That's all from my end. I will wait here for 5 minutes. I think nobody is asking question. I can end the session now.